Welcome to The Explainer. You ever wonder why a pot of water seems to take forever to boil? Or how sweating actually cools you down on a hot day? Well, the answers are hiding in plain sight in two key physics concepts. Today, we're unlocking the secrets of specific heat and something called latent heat, the hidden heat that makes the world work. Okay, let's jump right in. Everything we're going to talk about today, it all comes back to this one graph. Seriously. This shows the journey of H2O, all the way from solid ice to liquid water and finally up to steam. And as we add heat, the temperature climbs. That totally makes sense. But then it just flatlines. What is going on in those plateaus?
This right here, this is the big mystery we're solving today. You've got the stove on full blast, you're pumping energy into the system, but the thermometer just stops moving. Where's all that energy going? The answer tells us something huge about the difference between changing a substance's temperature and changing its actual state.
So, here's our game plan. We're going to follow the journey on that graph. First, we'll tackle the climbs. That's all about specific heat. Then we dive into the plateaus, and that's where we find latent heat. After that, we'll put it all together to crush some tricky problems, and finally, we'll dig into the deeper physics so you'll nail these concepts for good.
All right, first up, let's zoom in on the parts of the graph that are actually going up, the sloped bits. This is where our water is staying in one state, solid or liquid or gas, and it's just getting hotter. This is all controlled by something called specific heat capacity.
Okay, so the official name is specific heat capacity, and we call it C. The best way to think about it is like thermal inertia. It's basically a measure of how stubborn a material is when you try to change its temperature. If it has a high C value, it's really tough to heat up. A low C value, its temperature shoots up super easily. And this table just brings it to life. Just look at these numbers. Water is way up there at 4,200, while a metal like copper is down at 380. What does that mean? It means it takes over 10 times more energy to heat up a kilogram of water than the same amount of copper. And that's not just some trivia fact, it's exactly why we use water as a coolant in car engines. It can soak up a ton of heat before its own temperature really starts to climb. So let's put that formula to the test with a classic textbook problem. We've got a hunk of copper, and we want to know exactly how much energy it takes to heat it up. This is a perfect bread and butter specific heat capacity calculation. All right, let's break it down. First things first, we collect our data. Remember, physics formulas need standard units, so we have to convert those 590 grams into 0.590 kilograms. The C for copper is 390, and the temperature change, delta T, is just the final minus the initial, so 65 degrees. Now we just plug it all into our workhorse formula Q equals mc delta T, do the math, and we get just under 15,000 joules. And just like that, we've solved the first climb on our graph.
So we've handled the climbs. Now let's go back to our graph and take on the real puzzle, those plateaus. At 0 degrees and 100 degrees Celsius, the temperature just flatlines. Even though we're still pouring heat in, that energy isn't just disappearing. It's becoming latent or hidden, and it's doing something way more interesting than just raising the temperature.
The word latent really is the perfect way to think about it, because it means hidden. This hidden energy isn't making the molecules vibrate faster. That's what temperature is. No, this energy is being spent on a much bigger job. It's physically breaking the bonds that hold the molecules together. It's the energy of transformation. And that brings us to our second big idea, specific latent heat. We use a capital L for this one. It's the amount of energy you need to change the state of 1 kilogram of something. And the formula? It's beautifully simple. E equals ml. See what's missing? There's no delta T, no temperature change. Because on these plateaus, the temperature is totally locked in place. Now, latent heat basically comes in two flavors. First, you've got the latent heat of fusion. That's the energy you need for melting. Second, you have the latent heat of vaporization, the energy for boiling. And if you think back to our graph, that boiling plateau is way longer than the melting one. That's a massive clue right there. It takes a heck of a lot more energy to boil something than to melt it. And we'll find out why in a bit. So here's a nice, straightforward latent heat problem. The key thing to notice here is that the sulfur is already at its melting point. That's a hint. It means we don't have to worry about changing its temperature at all. We just need to figure out how much energy it takes to push it over the edge from solid to liquid. Let's run the numbers. It's the same process as before. We convert our mass to kilograms, we look up the latent heat of fusion for sulfur, and we use our new simple formula for state changes. E equals ml. A quick multiplication, and there's our answer. It takes about 3,000 joules of energy to melt that little bit of sulfur. Easy enough. Okay, so now we have two powerful tools in our physics toolbox: specific heat for when the temperature changes, and latent heat for when the state changes. So let's start combining them to solve the kind of complex, multi-step problems you're going to see in the real world and on your exams. All right, first up, mixing hot water with cold water. Now, there's no melting or boiling going on here, right? So we don't need latent heat. This whole puzzle is built on one of the most important laws in all of physics: the conservation of energy. Heat isn't created or destroyed, it just moves from the hot stuff to the cold stuff until everything evens out. The whole principle is as simple as this: the heat lost by the hot water has to equal the heat gained by the cold water. So we can write that as an equation. The mcΔT of the hot water equals the mcΔT of the cold water. The only thing we don't know in that entire setup is the final temperature, T. A little bit of algebra later, and we land on our answer, a final temperature of 48.1 degrees Celsius. And now for the main event. This is the ultimate challenge problem because it combines everything we've talked about: dropping ice into a warm drink. This is a classic question for a reason. It really forces you to slow down and track where all the energy is going step by step. The key to not getting overwhelmed by this is to just break it down. It's a two-step process. That's it. Step 1, that ice has to melt. That's a state change, so we know we need our latent heat formula. Step 2, where does the energy to melt the ice come from? It gets pulled out of the warm drink, which makes the drink get colder. That's a temperature change, so we'll need our specific heat formula. So let's run the numbers. Step 1, we melt the ice using E equals ml. That takes exactly 5,010 joules. Now for step 2, we use that number. We know the drink lost 5,010 joules of energy. So we plug that value for Q into the specific heat formula for the drink, and we solve for the one thing we don't know, the final temperature, T. And it works out to a perfectly cool 20 degrees Celsius. Okay, we've totally mastered the calculations. But to get you ready for those really tricky exam questions, the ones that go beyond just plugging in numbers, let's finish up by exploring the why behind all this. So why does boiling take so much more energy than melting? Think about what's actually happening. When ice melts into water, the energy just has to loosen the bonds enough so the molecules can slide past each other. It's like turning a rigid army formation into a milling crowd. But for boiling, you have to do two much harder things. First, you have to completely shatter those bonds and fling the molecules far apart from each other. And second, that new gas has to expand. And to do that, it has to physically push the entire Earth's atmosphere out of the way. That takes a massive amount of hidden energy. This same idea explains exactly why sweating cools you down. Just imagine the water molecules on your skin are at a huge party. The only ones that get to leave the party, the ones that evaporate, are the ones with the most energy, the hottest molecules. And when they leave, they take all that energy with them. This lowers the average energy of all the molecules left behind. And since temperature is just a measure of that average energy, the liquid left on your skin gets cooler. So in the end, this stuff isn't just about formulas on a test. Specific and latent heat are the invisible engines that shape our entire world. They're why coastal cities have milder weather. Thank you, water's high specific heat. They're why steam gives you a much worse burn than boiling water. It's releasing all that latent heat onto your skin. It's in the weather, it's in your kitchen, it's even in your own body. So now that you can see this hidden heat, what other everyday mysteries can you explain? Thanks for joining us on The Explainer.